Let's solve problem 8.7 for Microelectronic Circuits 8th edition by Sedra and Smith. This is a pretty hefty problem, but it does a great job showing how current mirrors and current steering affect circuits. So we're given this schematic, and we're told that it is fabricated in a CMOS technology for which mu NCox equals 400 microamps per volt squared, mu PCox equals 100 microamp per volt squared, Vt is equal to 0.5 volts, Va prime is equal to 6 microamp per micrometer, and all devices have length equal to 0.5 micrometer. We wish to design the circuit so that all of the currents labeled in this diagram have the currents that are given in the problem, and we want to use the minimum possible device widths needed, such that the current source Q2 operates with voltages at its drain as high as 0.8 volts, and to operate the current sink Q5 with voltages at its drain as low as negative 0.8 volts. Our goal is to find all of the widths for all of the devices. We want to calculate the value of R, and we also want to find the output resistance of the current source Q2 and the output resistance of the current sink Q5. So lots of things to find in this problem. Before we even start with the widths, I always recommend starting any problem like this with multiple transistors by labeling all of the PMOS and all of the NMOS devices. So remember that for an NMOS device, the arrow points at the bottom to signify that is the drain, the source, and then the opposite side is the drain. So the two NMOS devices in the circuit are Q4 and Q5, and then the other three devices, Q1, Q2, and Q3, are PMOS devices. Now we can begin analyzing the circuit. I want to actually start with this sentence. We want the current source Q2 to operate with voltages at its drain as high as 0.8 volts. Why is this important? Well, let's look at the circuit. So here's Q2. It's a PMOS, meaning that the 1 volts is applied to the source, and at the drain we can have a maximum voltage of 0.8 volts. So what does this tell us? Well, that means that the voltage from source to drain, the minimum of it would be 1 volt minus 0.8 volts. This is the smallest that the voltage across the source and drain can get. We also know that in order for a transistor to operate in saturation, the minimum voltage from source to drain across the PMOS is equal to the overdrive voltage. And this will help us with our first calculation. Let's keep going. So let's start by solving for the width of Q1, or W1. How can we solve this? Let me pose another question. What is the drain current for Q1, this current here? Well, we can see that Q1 forms a current mirror with Q2 because of this wire that connects the gates of each transistor together, as well as this diode connection between Q1, the gate, and drain. So this means that ID1 is equal to the reference current, because Q1 is our reference transistor, because it is the one that is diode connected. So we can use the saturation equation, ID equals 1/2 times mu PCox, since these are PMOS transistors, times the width divided by length of transistor 1 multiplied by V over drive squared. And again, V over drive squared is just equal to the minimum voltage across the source and drain, which we discussed in the previous slide, is equal to 1 volt minus 0.8 volts. So V over drive is equal to 0.2 volts, meaning I have all of the information I need to solve for W. So we'll go ahead and rearrange this equation. W over L for transistor 1 is equal to 2 Iref divided by mu PCox times V over drive squared, or 2 times Iref, which is 20 microamps, divided by mu PCox, 100 microamps per volt squared, multiplied by 0.2 volts squared. This is equal to, if we run the calculations, 10, meaning that W divided by L for Q1 is equal to 10. So if I want to solve for W, we can just multiply L to the other side. So W is equal to 10L. We are told that the lengths for all transistors are just 0.5 micrometers. So W is equal to 10 times 0.5 micrometers, specifically W subscript 1 to show that it is the first width. So we get that W for Q1 is equal to 5 micrometers. Let's continue with W2. Let's try to solve for the width of Q2 or W2 using our knowledge of current mirrors. So if I were to divide I2 by the reference current, that would be the equivalent of dividing the width divided by length of Q2 by the width divided by length of Q1. Now why can I say this? Because we've met two conditions. Q1 and Q2 have the same VT and also the same μp Cox parameters. So we do not have to go through the entire saturation current equation. We can instead just solve for W this way. So we'll say W divided by L for Q2 is equal to I2 divided by Iref times W over L for Q1. And you can see that this becomes a scaling factor. So if I plug in the numbers, it would be W over L for Q2 is equal to I2, which is 80 microamps, divided by the reference current, 20 microamps, multiplied by W over L for Q1, which we already solved for, that being 10. So you can see that this purely just becomes a scaling. We are scaling the width of Q2 by a factor of 4. So W over L for Q2 is equal to 80 divided by 20, which is 4 times 10, so 40, meaning W2 is equal to 40L, and L is equal to 0.5 micrometers, so that would make W2 20 micrometers. Let's continue with Q3. Alright, let's repeat the same procedure for the width of Q3, or W3. So if I divide I3 by my reference current again, that would be equivalent to the width divided by length of Q3 by the width divided by length of Q1. You may be asking, can you do this calculation with I3 divided by I2? The answer is yes, as long as both transistors are the same type, as in they're both NMOS devices or PMOS devices. So in this case, Q1, Q2, and Q3 are all matched PMOS transistors, so you can scale all these currents with the same mathematical modeling. But we will see that this is not the case for Q4 and Q5 because they are NMOS transistors. But we can proceed with W3. So W divided by L for Q3 is equal to I3 divided by Iref multiplied by the width divided by length parameter for Q1. And again, this is just purely scaling. So I3 is equal to 50 microamps. Iref is equal to 20 microamps. And W divided by L1 is equal to 10. So this is equal to 2.5 times 10, or 25. So therefore, W3 is equal to 25L, where L is still just 0.5 micrometers. So W3 is equal to 12.5 micrometers. Now let's move on to Q4. Next, let's solve for W4, the width across Q4. Now, we need to pause for a moment. We cannot do the same pattern we have been doing for the previous two widths because we are now dealing with NMOS devices. And the NMOS devices have a different mu n Cox parameter compared to mu p Cox. We also need to verify what the overdrive voltage is for the NMOS transistors. To do this, we look at this part. We want to operate the current sink Q5 with voltages at its drain as low as negative 0.8 volts. So if you look at Q5, and again, Q4 and Q5 are matched because they form a current mirror, with the reference being Q4, because it is the one that is diode connected. And we want the drain at Q5, the current sink, to be as low as negative 0.8 volts. And again, for these transistors to operate in saturation, we know that the voltage from drain to source, the minimum has to be equal to V over drive, meaning that VDS min is equal to VD min, which is negative 0.8 volts minus negative 1 volt from the source, which means that V over drive is in fact still equal to 0.2 volts. And so to solve for, let's say, the width of Q4, I4, that's equal to 50 microamps. And once again, we'll just need to use the saturation equation. So it's equal to 1/2, this time mu n Cox times W over L for Q4 times V over drive squared. So we have the rearranging of terms. So W over L4 is equal to 2 times 50 microamps divided by mu n Cox, 400 microamp per volt squared, times V over drive squared, 0.2 volts squared. And that is equal to 6.25, meaning that W is equal to 6.25 L, W4, where L is still just 0.5 micrometers, so W4 is equal to 3.125 micrometers. Now let's move on to W5. To solve for the width of Q5, W5, we can do the same scaling factor that we've been doing previously, but make sure that you scale it with I4 because Q5 is only matched to Q4. So we'll have I5 divided by I4 is equal to W over L for Q5 divided by W over L for Q4. So we get that W over L for Q5 is equal to I5 over I4 times W over L for Q4. And that's equal to, so I5 is 100 microamps, and I4 is 50 microamps, so that'll be 2 times WL4, and WL for Q4 was 6.25, so W over L for 5 will be equal to 2 times 6.25, and that is equal to, let me pull up my calculator, 12.5. Meaning that W5 is equal to 12.5 L, where L is still just 0.5 micrometers. So W5 will be equal to 6.25 micrometers. So we doubled the current, therefore we had to double the width. All right, let's move on to the rest of the problem. All right, so the next thing to solve for is the value of R. And let's try to do this using nodal analysis. So if I know the voltages on each end of the node and the current, which I already have, it's IREF, then I can solve for R. So we can see that one end is just grounded, so that's 0 volts. And what is this voltage at this node? Well, we can see that it's shorted to the gate of Q1 and Q2. So in other words, R would be equal to the voltage at the gate of Q1 or 2 minus 0 volts divided by IREF. So I just need to solve for the voltage at the gate of Q1 and 2. How can I do that? Well, I know that the voltage, the absolute value of the voltage from the source to gate of a PMOS is equal to the absolute value of its Thevenin voltage plus the absolute value of its V over drive, and I actually already have both of these terms. So the voltage from source to gate across these PMOS devices will be 0.5 volts plus 0.2 volts, which is 0.7 volts. So now to solve for the voltage at the gate, that would just be the voltage at the source minus that voltage drop, VSG. So that's going to be equal to 1 volt minus 0.7 volts. So the voltage at the gate is 3 volts. So now I can just solve for R pretty simply. It's just 0.3 volts divided by IREF, which was 20 microamps, yeah. So I get that R is equal to 15 kilo ohms. All right, let's move on to the last part of the problem. The last thing to solve for is the output resistances of the current source Q2 and the current sink Q5. So we'll start with Q2. Remember that this is a PMOS, so we can leverage the formula VA prime for PMOS, which is given to us, times the length of the transistor, divided by the current across the transistor. So for Q2, that is I2. So that's going to be 6 volt per micrometer. We'll take the absolute value of this term, multiplied by 0.5 micrometers, divided by I2, which is 80 microamps, and that's equal to 37.5 kiloohms. And similarly for RO5, we just need to note that it is a NMOS now, and the current going through this transistor would be I5. So we're going to use VA prime for an NMOS, which does happen to be the same value in this problem, divided by I5. So it'll be 6 volts per micrometer times 0.5 micrometers. And then this time I5 was 100 microamps. So we can expect this resistance to be a little bit less. And it is 30 kiloohms. And that completes this problem. Thank you for watching my video. For any questions or comments, feel free to leave them in the comments section or to email me. And have a great day.